Alright, let me begin by talking a little bit about linear transformations of column vectors. I apologize for the noise of the dishes in the background. Um, so just taking a step back from where we got to last time, I threw out the word isomorphism and said a little bit about what it meant. We proved it preserves dimension. We'll get back to that, but we're going to take a little detour here and talk about the matrix of a linear transformation for the most part today. I have a little bit more in terms of abstract linear algebra to tell you, but here's the little theorem that guides the next about 5 minutes of show and tell, if you will. So this proposition basically says that if we take a line segment and we map it under a linear transformation from Rn to Rm, then the image is either a line segment or a point. And the proof is straightforward, just basically feed the formula for the line segment. And we go from a line segment that goes from P to P plus V basically, to a new line segment that goes from T of P to T of P plus TV. So these purple are actually the line segment. And of course, if T of P is equal to T of V, then that actually shrinks to a point. So anyway, that basically guides understanding how linear transformations on Rn works. For example, here's if we multiply by the matrix K0, 0K, that's a dilation by K in both things. So we'll if K is positive, we like expand the square to a bigger square. The green maps to the green, orange maps to the orange, red maps to the red, purple maps to the purple. If we took K in both, if we made both of the, put K equal to -1, that gives us this matrix. Multiplying by that matrix defines a linear transformation, and that linear transformation is called inversion. Here's a picture. It takes the unit square and flips it over. So the point of what I'm doing right now is just to try to give you kind of a little bit of some kind of sense of what's possible for a linear transformation on the plane. What do they do? How do they behave? What can we see about them? I do hope you're reading my notes. I mean, I gave a bunch of examples of linear transformations I didn't have a chance to write on the board in class, and there's a lot of variety in those examples that I haven't gotten into in the lecture so far this semester. So I do hope you're reading along. Otherwise, you're kind of shortchanging yourself. But here's another one. 1, 2, 3, 4, then takes the unit square and maps it to this parallel piped. In particular, you might notice that L of E1 is where the lower line segment maps to. And it's no accident that L of E1 is the first column here, and L of E2 is the second column. That's the green maps. This E2 maps to that over there. Here's another one. This is a rotation by 45 degrees. Again, green maps to green, red maps to red is the thing I'm doing there. This one is very similar. Here, instead of having 1 over root 2, I've multiplied the previous one by root 2. So it's a rotation by 45 degrees and then a dilation by square root of 2. So it's like rotate and then this is an arbitrary rotation. So if you want to like rotate by theta degrees, or excuse me, theta radians, I should say, then this matrix will do it for you. And you can, conversely, you could take this picture and derive the matrix from doing trigonometry on this picture if you were so inclined. This is the identity matrix. It gives you the identity transformation, and I don't know why I used so much of space in the notes to put that picture there, but there it is, identity transformation. Exciting, yeah? This one's a little more exciting. Here we have the P1 and P2. They're defined by basically killing y, sending all the y's to 0 or sending all the x's to 0. And so these are both what are called projections. And the second projection, why my daughter's singing right now, I don't know why. But anyway, projection 2 just sends these red lines to these dots. And projection 1 kills off the y component, so it sends all these vertical lines to this dot or that dot. And so projection loses dimension. Here's another one that's a little bit kind of harder to follow. 1, 1, 1, 1. So again, this matrix is not invertible. And it's no accident that this non-invertible matrix corresponds to a linear transformation, which takes the square and squishes it to a line. So what I tried to illustrate here was both the red and the green lines mapped to the line segment from 0, 0 to 1, 1 over here. But the other two end up covering this later part of the line. Now, you could also look at higher dimensional examples. So here's a mapping that goes from R2 to R3, and you can think about this as like pasting the unit square into that unit square. My next example, we have 1, 1, 0, 1, 1, 1 for the matrix of the transformation. I realize we haven't defined that yet, but you'll forgive me. The next video, we prove the fundamental theorem of linear algebra, which shows, in short, that if it's a linear transformation of column vectors, then there exists a matrix called the standard matrix, which you can write the formula like that in terms of. Anyway, so this one, if we think about it, we could think about mapping the unit cube, and this unit cube, I worked it out, the front face here actually maps to that upper parallelogram, like blue goes to blue, green goes to green, red goes to, the red dot goes to red dot, orange dot goes to the orange dot. I think I have some color coding in the original PDF, but my color printing is, well, not so awesome right now. In fact, it's pretty much non-existent. And then here's a fun 4-dimensional to 2-dimensional. So this maps from R4 to R2, and I have a silly picture, which I don't have in front of me at the moment. So yeah, there's some examples of linear transformations, and I'll start again by proving the fundamental theorem of linear algebra. And then we'll go on to look at a few more things about linear transformations today.